Hello, everybody. Welcome to Duke Spark seminar. My name is Maciej Mazurowski. I am a faculty at Duke University. Duke Spark is an initiative here that focuses on research and implementation of medical imaging AI algorithms. You can see our website here, some social media. Feel free to get in touch with us if you're interested in this kind of endeavor. I have a pleasure today of welcoming Dr. Alexander Wong. He is a professor at the University of Waterloo and Canada Research Chair in AI and Medical Imaging. His research focuses on ethical and trustworthy AI, as well as computational medical imaging. Looking forward to your presentation. Alex, please take it away.
Perfect. Thank you for the opportunity to give this presentation. I'm going to try to share my slides right now. And let me know if do you see my slides?
I do, yeah.
Perfect. So I'm going to get started then. So thank you for the opportunity to, I guess, talk about some of my work in this area. In particular, today, I'm going to focus on essentially a transparent and trust-centric design approach to AI for healthcare. So as we all know, there's been significant advances and promises in AI for healthcare, and AI has been slowly but surely being adopted in the medical field. So you have examples where there's AI-powered CAD systems that are actually now being deployed and directly into clinical applications, from Eika's Ruby to Siemens AI Red Companion. It's been leveraged for AI-powered radiomics, genomics, pathiomics, and so on and so forth, as well as for drug discovery. So there's been a lot going on in the field of AI for healthcare, right? And also in that light, what we've done was we've also made quite a lot of advances in our own research lab, one of which is the COVIDNet initiative. So the COVIDNet initiative is a global deep learning initiative for supporting COVID-19 clinical decision support. And there's some unique characteristics about it. One is that it's completely open source, open access. You could actually, here's the link, and you could reach all of the information through our portal. We continuously improve it and have regular releases of new models and data to help support the actual research community. It started off as a team of two people, myself, as well as my student at the time, Linda Wang. And now it's grown to be the most widely used open AI model of its kind for COVID-19 in the world for research, and now used around the world on all continents by researchers as well as scientists, which we're very happy and proud of. And it started with just detection and risk stratification from chest radiography, has now grown to cover a much broader range of clinical decision support tasks and clinical integration tools and clinical decision support platforms, from diagnosis to risk stratification, all the way to treatment planning. And we receive a lot of global support. Our team is significantly larger now, and we're fortunate to have received a lot of media coverage. And one of our main goals with the COVIDNet initiative was we would like to promote open models and open data for all, especially during the pandemic, where this information was very scarce. There's not a lot of resources going around. So we put a lot of effort in creating the world's largest data sets for different modalities, from chest x-rays to CT scans to ultrasounds and so on and so forth, as well as all the supporting models for supporting different clinical tasks, from severity scoring to treatment planning, case management, COVIDNet classification, so on and so forth. And so we've since expanded the project into a new initiative called CancerNet, which is a global deep learning initiative for supporting cancer clinical decision support. Once again, everything is open source, everything is open access, and we continuously improve and release new models and data. We currently have the largest open data for CDI imaging of various cancers in the world to support researchers around the world, all driven by trustworthy and explainable AI covering a broad range of clinical decision support tasks from diagnosis to prognosis to treatment planning. And we're also very fortunate to receive a lot of global support as well as media coverage. So everything sounds good and all, but then the question here is, if AI is so promising for healthcare, why don't we use AI all the time by now? And based on the numerous extensive collaborations I've had with enterprises in different sectors, not just in healthcare, but also in automotive, transportation, aerospace, consumer electronics, finance, agriculture, and so on and so forth, there's been a very common message amongst industry, especially in healthcare, that AI, especially deep learning, is game-changing, but full of challenges to widespread adoption across industries in reality. So there's been a big gap between translation from promise to impact. And one of the biggest challenges that has always been raised to leveraging AI solutions in real-world practice, especially in healthcare, has been the notion of trust. So here's a very simple example that I guess went really viral, was that there was a viral video where it was a soccer match, and during the entire soccer match, the camera was not focusing on the ball. In many cases, it couldn't even see the ball, but it was actually focusing on the referee the whole time. So it kept tracking where the referee is, completely ignoring the actual game itself. And what was found was that the AI algorithm, which was put into the wild, was actually not tracking the ball, but tracking the bald head of the referee as though it's a ball. And so these are perfect examples of where, when AI is released into the wild without additional checks and balances, things can go quite wrong. And that's where reality really sets in. And the bigger issue when applied to healthcare is that when trust breaks down, it becomes it can have very, very negative social economic impact. So a good example here is this algorithm that was actually an AI algorithm that was built for understanding or making decisions on the amount of healthcare was to be given to individuals, was actually showing significant biases against African-American demographic. And what they found was that it was actually a data problem where the data itself was largely biased from historical data, where that group actually just received less healthcare, right? And as a result, AI, like the child, learns about these biases without understanding there's an inherent bias. And that's where an AI system that is used to screen millions of people each year actually had a very, very big bias that was causing a lot of social impact. And on the right-hand side, it's a more recent development with the development of, I guess, adversarial attacks and so on and so forth. People are now looking into situations where healthcare data can actually be compromised, where trust can be compromised by bad actors. And so as a result, being able to build and deploy AI solutions in healthcare has been very challenging in practice because of these issues with trust. And so a lot of companies, including healthcare companies, had the more wait and see mentality. They'll say, okay, we'll deploy it and we'll see how things behave in the wild. But now it's no longer about wait and see. There are actually now regulatory consequences with the deployment of AI in the wild in a unchecked manner. So recently in Canada, we have the Canadian Digital Charter, C27, where part of it is focused on algorithmic transparency, where an algorithm or AI is being leveraged to make a decision on an individual. They have the right to question and ask, why was that decision made? In the European Union, one of the biggest things was that their Artificial Intelligence Act, the AIA, has recently become law, and now there are fines up to 30 million euros or 6% of global revenue. So it's a very large penalty that companies are now really waking up to when it comes to AI deployment. And in the US, there's the Federal Trade Commission, so FTC, where they've mentioned that we will, if you don't hold yourself accountable, be ready for the FTC to do it for you. And so now it's no longer wait and see. Compliance is now a global must. And a big part of compliance across the world has been the need for explainable AI. So with all of these different challenges of trust, one might think, maybe we just won't deploy, AI for healthcare, right? There's just too many hurdles. But fortunately, significant advances and progress has been made towards the notion of trustworthy and trust-centric design of AI. And a number of these different aspects include quantitative explainable AI, which is why does an AI actually make a certain decision that it makes, right? There's the notion of trust quantification that's become a lot more popular in recent years, is where when can we actually trust an AI and where are the biases and gaps in fairness? Another way to improve the trust in AI is to improve the actual medical imaging modalities itself to allow for better trust through better data. Another aspect I'm also going to talk about is now leveraging something a little contradictory, is leveraging actually generative AI to actually improve the trustworthiness and reliability of these AI systems that we can build. And last but not least, where humans really come in, is best practices and ethical considerations in terms of how should I design trustworthy AI. So let's actually talk about the notion of explainable AI first. So on the high level, today, most of our AI algorithms are based on the notion, especially in machine learning, where we have training data. There's a machine learning process. It learns from the data and creates a machine learning model, which we call here learned function, which makes a decision and a recommendation to a user. But the problem with this is that it has a very black box notion around it, a nature around it. And so even though you're getting a decision or recommendation, why did it make a decision that it made? Why did it not make a different decision? When does it actually succeed? When does the AI fail? When can we trust the AI? And more importantly, how do I actually correct the errors that are being made by AI so they don't make it anymore? So that's been a huge challenge in recent years towards trustworthy AI. And so what explainable AI allows for is that you're still training with data, you're still creating a machine learning process, but now you have explainable models and, more importantly, explainable interfaces that interact in the human-machine collaboration perspective with the end user. And in the clinical case, it would be with clinicians, healthcare workers, and so on and so forth. And with explainable AI, we could now understand why it made a certain recommendation or prediction, understand why it didn't make another one, understand when the actual AI solution actually succeeds, when it fails, when can you trust it, and more importantly, if it makes errors, be able to identify it and know why it made error so you can take actionable steps to correct for the error. And so what exactly is quantitative explainable AI, which is one of my main focuses? So the notion around quantitative explainable AI is to move away from the notion of XAI as a buzzword. Right now, a lot of times we talk about explainable AI, but what does it really mean, right? So how do we actually move it from theory to actionable insights, from proxy to direct explanations? So with a lot of explainable AI methods that you see right now, a lot of them just give you kind of like a heat map where, here it might be a little bit more important, here it might be a little less important, and so on and so forth. So then the question is, how much more important is this particular area? How much less important is this particular area? Does this actually important area actually lead to a better decision? And more importantly, does the actual factors that are being identified actually have a strong influence on the actual decision-making process itself? And so with current explainable AI approaches, it's pretty much in itself kind of a black box and requires a lot of human interpretation. So it's not really a true explanation. So with quantitative explainability, what we're trying to do is, can we produce concise, exact, concrete explanations, as well as provide a quantitative justification around it? So here's a very simple example of a image classification case, right? There's a bunch of images, and the underlying AI model is making a decision on what it is, right? So with quantitative explainability, the quantitative explanation is what you see in the middle column, where instead of saying, this is a little more important, this is a little less important, it'll tell you the exact area, what you see highlighted, that actually led to the actual decision that this is a warplane, right? And not only that, it actually provides a quantitative justification around it. So what it provides is, based on this explanation, the model predicts it is a warplane with 98.7% certainty. So it's really sure about it. Because otherwise, the model would actually predict that it's a parachute with a 5% certainty. So as you can see, not only do you know exactly what are the factors that led to decisions, you also have a deeper understanding into why it actually leveraged that to make the decision and not something else. Similarly, for the meerkat, what you see is that with the quantum explanation, what you see is the exact location that actually led to this particular decision, which is the face as well as the front of the fur, right? And based on this explanation, the model predicts it's a meerkat with 97.4% certainty, because otherwise, if it's leveraging any other kind of visual cues in this case, it would actually predict that it is an ostrich with 67.6% certainty. And if you were to actually like put your thumb up and kind of cover where the meerkat is and kind of look at the surrounding region, it's not a stretch in the imagination that it kind of would kind of lead to a decision where maybe it kind of looks like ostrich because of the grass around it, and it's because it's elongated, so therefore chances are it might have a long neck. So now you can actually have a much deeper understanding into the decision being made through this type of quantitative explainability. So that's on the high level. So then the question is, why do we actually need quantitative explainability? The reason we need quantitative explainability is because it allows you to deal with a lot of situations where you can do the proper checks and balances to ensure that your AI is doing the right thing. And so there's actually a number of different use cases around that. One of which is quantitative explainability allows you to ensure that the right decisions are being made for the right reasons. So here's an example on the left where we build an AI model for predicting the severity of lung degradation for pulmonary fibrosis. And so what's able to do is show you the exact relevant visual indicator in the lung that led the model to make that prediction that this is in fact somebody who's going to have very, very bad lung disease severity. And what you see here is that highlighted there is the actual honeycombing that's actually happening in the lungs. And so with this information, a radiologist can make a much better, much more concrete decision and also guide them through the whole volume of data. This is a CAT scan to look at specific locations to help them make better and more accurate and more consistent decisions. On the right-hand side is a case where it's a chest X-ray, where it's able to show the actual ground glass opacities in the lungs to help it better identify COVID-19 severity. So by looking at this, a radiologist, as well as the developers of the AI, can be much more assured that the AI is actually making the right decision for the right reasons. So this particular example, this application is very clear, right? Very obvious. But what about ones that are not obvious, but are equally, if not more important? So another reason why we want quantitative explainability is to identify reasons behind wrong decisions. So here's an example that's non-medical, just to help give context, is on the left-hand side was identified the explainable AI that there is an inherent problem here. So the model thinks that this person, this pedestrian, which is labeled as pedestrian, thinks it's actually a cyclist. And because of explainable AI, what you see is the reason it thinks it is a cyclist is that you'll see highlighted that you have a bicycle where the person overlaps. And so in its mind, the AI is thinking, okay, here's the person, here is a bike, the person is overlapping the bike. As a result, it is a cyclist, right? And with this kind of insight, what we're able to do is take actionable steps to show it more example, so it understands that even in this kind of situation, that this is a pedestrian and not a cyclist. In the middle is a very good example of where human error can really come into play. Here, the explainable AI is able to highlight that these are all the situations where the model actually made correct detections of the pedestrians, but there were actually no human annotation associated with them. And as a result, the model, even though it's making a right decision, is now being penalized because of human error and laziness. And so this is a situation where you take the data, give it back to the original annotators and say, hey, you missed something, you annotate it. That's how you can actually improve the performance of the model. In a more clinical related case, on the right-hand side is an example where the model was actually making a misdiagnosis because it's not looking at the person. This is an X-ray of a person's lungs. It was not looking at the person's lungs. It was not even looking at the person. It was actually making a diagnostic decision based on embedded text in the X-ray, which definitely is incorrect. And so actionable steps can be taken to identify and to correct for these wrong decisions. And last but not least, the third one, which I always find the most interesting, is to help us identify situations where the right decisions are made for the wrong reasons. Usually you look at things like sensitivity, specificity, and if things look good, then you would deploy things into the wild. But what could happen is that your AI model can actually be making all the right decisions, but for all the wrong reasons. So here's some very clear examples around that. So on the left-hand side was when we were building a model for detecting COVID-19 from CT scans. And so we were getting like fantastic sensitivity, specificity, close to perfect, right? Close to 100%. But what we did was we did additional auditing using quantitative explainability. And then as soon as we saw the explanations, what we did was we threw all our results, all our models out the door and started from scratch. And the reason for this was the model was very, very good at detecting COVID-19 by never looking at the patient, never looking at the patient lungs, but by always looking at the patient bed they were lying on, which is completely ridiculous. And so again, this is a situation where it's making the right decisions, but for absolutely atrocious reasons. And as anyone can guess, what's the actionable step that we took to greatly improve the model performance? What we did was we took all the data and we removed the beds, and lo and behold, once it learns and trains, it still gets very good sensitivity, specificity, not perfect, but based on the explanations, it was always looking at lungs. It was looking at the ground glass opacities, bilateral abnormalities, and so on and so forth. So now you have a model that not only has great performance, but also does it for the right reason. On the right-hand side is a case where another model that was being built correctly detected disease, not based, again, on the patient's anatomy, but based on imaging artifacts. And so these are situations that are very hard to detect, right? That quantitative explainability can really help with, to really help identify what the root cause for the problem is, even though it's making the right decision. And we've since expanded this even further. So with quantitative explainability, what you see is that it's instance level explainability. So given a particular patient, given a particular image, here is the explanation on the decisions. But on a high level, because of the wealth of information that's out there, what we thought is, can we actually use the wealth of explanations that we get to learn more about and get a deeper understanding into how an AI model actually behaves? So that's where we introduced the notion of second order explainability, where we're actually trying to explain explainability itself. So the goal here is, can we explain explainability by looking at the core trends, concepts, and patterns that the AI leverages to make decisions based on not just a specific instance, but based on the plethora of explanation across different data sets. So at a data set level versus at an instance level. So here's an example where we took second order explainability and we used it to really understand how an AI was making decisions for severity assessment. And what we found was it was actually leveraging two main concepts. On the left-hand side, what you see is it was relying on ground glass opacities. On the right-hand side, you showed that it was really leveraging honeycombing patterns. And this type of analysis not only allows us to understand our models better to help us improve the model, but it also gives clinicians new insights into what might be important things to really look for a given disease. Another concept that we've looked into that is getting widespread adoption is the notion of trust quantification. So a lot of times when you're building machine learning models, especially deep neural networks, what tends to happen is that it is overconfident about every single thing, every single decision that it makes. So whether or not it gets the right or wrong decision, you get like 99% confidence that they are right, even though they're not. Right? And so this causes a lot of mistrust, because here it's the equivalent of having somebody who always tells you an answer and always does it in a very convincing way, kind of like ChatGPT, but has no notion of whether it's right or wrong, any sense of truth. So what we've done is we've created new approaches for actually understanding when an AI is overconfident, when it's not, so that we can have better assessment on the overall trustworthiness of the decisions being made. Right? And in general, by using that information, we're able to build better AI models that are confident when it's correct, but cautious when it is not quite sure. And we've had a lot of success improving the overall reliability on not only the decisions being made, but also the actual level of certainty or confidence that the AI has in their overall decisions. Right? And so using all of these different types of concepts in explainability, trust quantification, and so on and so forth, what we've done is build and introduce an explainability-driven design framework for improving and building tailored models with trusted, clinically relevant predictions and sound rationale. So in a nutshell, what we do is we start off with like a generic model, right? That might have unclear predictions and rationale. We go through a clinically guided initial design phase. Then what we do is we go through a explainability-driven design refinement phase where an explainability analysis is done on the model to identify what are the key biomarkers being used, what are the key factors being used, what kind of biases might be inherent based on demographic, gender, sex, and so on and so forth. Then we consult with clinicians to really understand, is it using the right factors? Are there certain factors that are just not relevant that it's using? Are there certain factors that it's putting in that's really doing a good job? Is it showing any kind of biases between different demographics? And based on that, the model can then get refined so that it hones in on the relevant information to not only improve accuracy, but also efficiency and consistency of its overall decisions, and present it in a way that clinicians can really trust and believe in the results being presented. So what are some of the use cases? So one use case that we did was on drug discovery, where given a patient's gene expression and drug molecule, to be able to predict the patient's response for a given disease. So usually you get high performance there and then you call it a day. But what we did was then we leveraged explainability as well as second order explainability to really enable the discovery of key genetic factors driving the drug response. So what you see on the bottom right was that we're able to identify not only the most predictive genetic factors that's indicative of drug response for cancer patients, so that we could hone in and build a better model around it, as well as give new insights to clinicians and clinical scientists. We're also able to identify different genetic factors that not only didn't contribute to the prediction, but actually had a negative impact on the prediction capabilities of the actually underlying model. We've also applied it to the notion of AI-powered clinical ICU admission prediction, where the underlying goal is to predict whether an individual needs to receive ICU admission given the current patient profile. And so we're able to leverage explainability to improve the AI model design while gaining system-level insights. So we're able to identify what are the key factors necessary. Is it the heart rate, sodium levels, so on and so forth, bilirubin levels, so on and so forth, that gives us a good indication that this individual really needs ICU admission, as well as identify things that are that might be actually confusing the actual AI model. Not only that, with trust assessment, we're also able to garner a much deeper understanding of potential demographic biases. So in this particular case, what we did was we analyzed the trustworthiness of the model when it comes to gender. It's actually quite fair in terms of this model, as well as related to age. In this case, it's also very fair, right? But we've also run into other situations where we're building models and we're able to find not only gender or sex types of, anomalies and inequalities in the trustworthiness of the decision being made. We've also seen situations where education actually had a big factor. So individuals in that high school education was not treating as trustworthy decisions being made compared to individuals with university level education, grad school education, and so on and so forth. So these kind of insights allow us to really identify and understand the overall behavior of the AI model itself and find corrective mechanisms, be it identify what are the key factors to use, what are the things that we should exclude, right? Including things like age, education, and so on and so forth, so that we not only have a better model, but we also have a better corpus of data to build these models around. From an explainability perspective, we've leveraged it for clinical decision support for diabetic retinopathy. When dealing with clinicians, right, radiologists, ophthalmologists, and so on and so forth, to give them just a prediction from an AI, it's usually a no-go, right? Imagine you're a clinician and suddenly you have an AI system just tells you this person has cancer. And when you ask it why, you say, I don't know, but I just know this person has cancer. There's going to be very little trust in this AI system because there's no rationale or explanation around its decision-making process. So what we've done was build clinical decision support systems that incorporate quantitative explainability to allow us to not only have better insights to make better predictions, but also allow the clinician to be in control of the situation, to distill information to help them make a better decision. And we found that clinicians have really appreciated this approach because it's really about helping them improve patient care, patient decision support, right? So here in this case, here using explainability, we could gain deeper insights and transparency into the decision-making process of the AI with the aid to allow them to have knowledge discovery and clinical decision access, right? And so in this case, for diabetic retinopathy, rather than telling them, okay, this person has, a mild case of diabetic retinopathy, a severe case of DR, moderate case, and so on and so forth, which really doesn't help the clinician, what we show is, okay, these are the different areas identified by the AI that you should be concerned with. There are certain regions here where it's showing signs of moderate DR. There are other areas where it shows negative. There's other areas where it thinks there's a mild response. And so instead of just giving one particular prediction, it shows all the predictions as well as all the rationale behind it. And so what we found with a system like this was that the clinicians are not only more appreciative, they don't really care much about the actual decision being made itself. They care more about the explanations being provided because it's these explanations that allow them to identify key areas for them to focus on in their own clinical decision-making process. And so this allows for a lot of greater accountability as well as much more advanced reporting to clinicians. We've also applied, this kind of trust-centric, transparency-centric approach to AI design to fibrosis progression prediction. So here in this case, we're building a multimodal deep learning system for predicting pulmonary fibrosis progression from chest CTs and clinical data. And what we found was that even though when we receive the data, we're under the assumption that the data has been cleansed, has been cleaned, so on and so forth, what we did during our explainability-driven data auditing process was we uncovered a significant amount of data issues that were previously not known. And these undiscovered data quality issues can really lead to very useless models with great numbers, so great sensitivity, specificity, and so on and so forth, but ridiculous decision-making rationale. And so with explainability-driven data auditing, it allows us to identify actionable insights on how to actually not only improve the model, but to improve the actual data quality itself. And this actually allow us to, with our FIBROSIS-Net project, get not only state-of-the-art performance that outperform all other solutions out there, but also get correct, trustworthy predictions along the way. And so on the top right-hand side, what you see is that it was able, during the explainability-driven data auditing process, identify unnecessary padding that were baked into the DICOM, identify artifacts that was leveraging to make decisions, and we were able to even identify DICOM header information that was just incorrect, but was leading to biases in the actual decision-making process. And when we got rid of all of these to create a really high-quality data set, it allowed the models to really understand and make better decisions, as you see on the bottom right, where it was able to identify the key honeycombing patterns that were leading to proper predictive processes for fibrosis progression. We've also applied it to COVID-19 screening. And what we found was that by having explainability directly in the actual user interface, it really allowed for validation by clinical experts to ensure decision-making processes were actually consistent and correct with clinical interpretation. So rather than us as AI scientists just trying to think, okay, we know better than clinicians, when we look at the results, it's correct, so therefore it should be ready to use, having an explainability-driven UI allows clinicians to give the right feedback, so as well as the right level of trust, so that they're not only comfortable with the AI itself, but comfortable with the interface itself. So here, what you see is our COVID-Net, medical imaging viewing platform, which is available open source for anyone to use and build upon. So not only do we actually show what the results are in terms of what its predictions are, in terms of geographic severity, geographic extent, opacity, and so on and so forth, it actually highlights the key areas In this case, it highlights the bilateral patchy opacities as the key indicators as to why this person has a high likelihood of having COVID-19. We've done this also for COVID-19 risk stratification. So identifying the key areas in the lung and associating them to understand, does this person have what type of lung airspace disease they have? Is it severe? Is it mild? Is it moderate? And so on and so forth. And again, this really allows for high performance and interpretable clinical decision support systems that are trusted by clinicians to aid in their decision-making process. Okay, so that's on actually the more on the AI front, right? But again, AI isn't magic. And one of the things that we really need to realize that I always teach my students is that it's not, if it's something is not in the image, no AI can magically eke it out and find it. Garbage in, garbage out, right? A lot of times people try to, okay, I'm going to tweak this model. Oh, and performance increases by this much. Great. But it's really about looking at the data, really understanding what you're dealing with, understanding what it can do, understand what the modality can't do. So in the middle, what you see is a perfect example of that, where we have a MRI of a prostate. And what you see here is that there is actually a very, very large high-grade tumor right in the middle of the central zone. However, what you can see is that nobody can actually see it in this mode. It's actually completely in stealth mode and hidden. And if you were to show it to radiologists, which we did, they are not able to actually see where the tumor is at all. Yet we know there's a tumor there for sure because a biopsy was actually done, right? So what this illustrates is that if a radiologist cannot actually see anything in it, and you can't see anything in it, chances are AI is not going to magically be able to uncover it. And that's where improved imaging modalities can greatly improve the trustworthiness and reliability of AI. So one great example is, hey, what if we improved it? So we were dealing in this case where we have MRI, and we're like, okay, great, this is not useful for building AI. What can we do instead? So what we did was we created a new form of MRI called correlated diffusion imaging, specifically for targeting cancer itself. Based on the tissue characteristics of cancer, we're able to build new pulse sequences that allow us to really, really highlight where the cancer is. So what you see on the right is we overlay correlated diffusion imaging information on top of traditional MRI. And what you can see highlighted in red is the exact location of that tumor that we're just talking about. And not only where it is, but the exact margin, which is very important for localization as well as focal therapy, right? Where instead of removing the entire gland, what they're able to then do is actually just destroy the tissue around that red area and allow for much better recovery in maintaining full functionality. And so this is a very good example where by improving the actual imaging modality catered around what you're trying to detect, it also allows you to build much better AI. On the bottom case is where, when given our initial success with correlated diffusion imaging for prostate, we've since expanded it for the purpose of breast cancer. And so on the bottom are CDI imaging information overlaid for breast cancer. And we've been very successful in not only detecting the underlying severity of the actual breast cancer, but also identifying predicting whether a particular patient will actually respond well to a given chemotherapy treatment. And so once again, you can build much better AI when you have much better data, even if it requires to build a brand new imaging modality to suit that need, right? We've since applied this modality beyond cancer. To a surprise, it actually worked very well in understanding white matter microstructural abnormalities in the brain that other types of MRI modalities was not able to be sensitive at all. So we were actually quite happy about this particular study, and we recently published it. And so as you can see, once you build better imaging modalities, it's limitless in terms of the number of applications that you might discover along the way. More recently, what we've done is, given the fact that we're able to create all this large amount of data, one of the key limitations now is that the data is often imbalanced. So there are real world distributions there's real world data scarcity, so you'll never get a perfectly balanced data set ever when it comes to medical imaging. And that's where we found that generative AI can help. So what we did was we've been exploring different ways of leveraging generative AI to actually fill in the gaps and build a larger, more balanced corpus, and in a way that allows us to target specific grades of cancer. So for example, here you see that it's being generating, MRI images for different cancers at different locations and different grades. And this improves the data distribution and diversity and can greatly improve the trustworthiness as well as the reliability of AI. So to end this talk, last but not least, a very important part beyond just AI technology and so on and so forth is human interaction, right? So the human in the loop. So employing best practices as well as ethical considerations become very important for building AI that are trustworthy as well as transparent, especially in critical applications such as healthcare. So things like accountability becomes very important. We need to understand that AI make autonomous decisions, but the creator at the end of the day is responsible for the outcome. So understanding the seriousness of proper AI deployment becomes important, because at the end of the day, when a clinical decision is being made, that could be life critical, right? You can't just say it is the AI's fault, right? Transparency, as I mentioned, is a very important part in best practices and ethical considerations. Different AI methods have different levels of transparency. So really understanding the right method for the right task at the right level of transparency become very important, be it for, based on EHR, EMR data, medical imaging data, so on and so forth. Understanding what level of explainability you could get out of it becomes important for really understanding the systems that you build. Data provenance becomes important. As I mentioned, AI is only as good as the data used to train it. So really understand the data and the limitations of the trained model. You have no idea how many situations where I talk to individuals where they built the entire AI by never looking at data, but looking at the performance metrics. The performance metrics, a scalar number will only tell you so much as to how your AI is actually behaving. In many cases, very little. Bias becomes very important. We really need to understand and identify, test for, and mitigate potential biases in data and model. And explainability becomes a very core part of it. Data leakage becomes important. We need to make sure we identify the predictors that can appear to be random, but actually lead to predictions in a biased way. So things like black bars used in padding, image watermarks, embedded text in X-rays, and so on and so forth. And last but not least, things like class imbalance becomes important. Training data is often imbalanced. So really understand the nature and the limitations of AI when trained on imbalanced data, as well as ways to mitigate these imbalances becomes important. Because if left unchecked, it could have very serious ramifications. So recently, there was a data set that was released as part of a challenge, and people were building models around it. Everyone was getting 90-something plus accuracy, right? But is it actually correct? The answer was no, because the data itself had 90-something% of the patients being benign and only a small fraction of them actually having the disease. So as a result, what I can do is forget about AI. I could just build a very simple rule and say everybody is benign, and that would achieve 90-something% accuracy. And that's why really understanding your data and the imbalances becomes very important. And so just some final thoughts. For me, AI really holds tremendous promises and potential for clinical decision support in healthcare. However, there are tremendous real-world challenges to achieving trusted AI. Fortunately, a lot of progress and advances have been made towards transparency and trust-centric AI design, things like quantitative explainability, trust quantification, improving imaging modalities, leveraging generative AI to improve balances, and really employing best practices and ethical considerations in building AI. And in general, in my opinion, I deeply believe this, that the benefits really outweigh the challenges in designing, operationalizing trusted AI solutions for the healthcare space. So thank you very much for listening to this talk.
Thank you, Alex. Great talk. So we have a few questions here. Maybe let me start. I have a quite general question to you. What do you think that the main reason is why there is not more clinically implemented AI algorithms in medical imaging. And I wonder what weight do you assign to the aspects of technology and evaluation, so that maybe the technology is not good enough yet, regulatory questions, right, and maybe trustworthiness being part of those, or the first aspect, and then the third aspect being potentially not being able to make a business case for some of those algorithms. And I understand that some of the answer might be different for different countries. But so what are your thoughts on that?
So yeah, so a couple of things. So for me, there's a number of different factors that is kind of delaying widespread adoption. For me, trust becomes very important, especially when regulatory processes are being in place. That's one. So the other key thing is that the road to FDA approval or Health Canada approval, whatever your regulatory body is, getting approval is a very, very, very long road. And so a lot of companies, especially startups, aren't able to survive until the very end because of all these procedures and so on and so forth. And that's another key one. The other one that I would really like to highlight is that it's terribly difficult to get good data, right? So anyone who's been building AI for healthcare knows that a lot of times our data is very siloed. You have small pockets of data that is not really truly representative of the general population, but that's all you get because you spent months trying to get secondary data transfer agreements in place, trying to get a hospital convinced that AI has value, trying to get through all the ethical governance, privacy kind of procedures. And so just even getting access to the data becomes extremely challenging. And once you get the data, because it's small pockets of data, you have to start a data sparsity problem, as well as a situation where your data is not really too balanced. And so even if you're able to build an AI out of it, it might not generalize. We've seen many cases. For example, there was one case where Google, deployed a system for eye imaging, right, for eye disease, ocular disease analysis. And what they found was that in those countries that was being deployed, the whole system was just not working. And the reason for this was the imaging procedure, and everything was very different in those countries, where whatever they trained with, the pockets of data were able to train it, just didn't generalize at all to those particular cases. So these are all the different hurdles that have really delayed, widespread adoption of AI. But I think a lot of progress is being made right now.
All right, thank you. So let me read some questions from the audience. One question here is for the example that you mentioned, that make right decision and get high performance based on wrong evidence. If there's possible that there are hidden relationships between this evidence and the decision. Also, if we narrow the model to only emphasize the features we want at the beginning, how to compare a DL model with the traditional ML model, such as feature learning models, decision trees?
So very good question. So I'll answer the first part, is that is it possible there's hidden relations between evidence and decisions? In this specific case that I illustrate, the answer is no, right? There really is no proper relationship with a hospital bed, right? That one's no. However, we had other situations where there is, in fact, a hidden relationship, right? And at first, we thought it was an incorrect relationship. But as AI scientists, we don't know any better. So we ran it by the clinician. And what the clinician found was that was actually very surprising and very interesting, was that, oh, wow, okay, I didn't think this was important. But in hindsight, if I think through it, this could actually be a very useful visual indicator. And they start adopting that. And so for us, that's where explainability comes in place, where it was able to identify where it made the right decision for something that we thought was the wrong evidence. But when we checked with the clinician, in hindsight, it actually ended up being the right evidence. So that was a very interesting case. So in the second one is that if we narrow the model to only emphasize features that we want at the beginning, how to compare. So one of the key things that we try to do is we don't try to narrow down what features or what types of factors for it to look at. When we first start off, we try to expose it to the all available health information that's possible, because we would like to then use explainability to help us identify what is actually particularly relevant, what is really having a huge influence over the decision, and then we run it by the clinician, right? So that's a bit different. So in terms of how to compare DL and model with traditional ML models, such as feature learning and so on and so forth, what you can do is, what people don't appreciate is that even with deep learning, right, it's not always just about pure feature learning. You could actually influence the types of features that it actually learns based on how you manipulate the actual input. And so what we do is we leverage explainability to go back and manipulate what the input should be so that it guides it towards a better decision, and it allows it to learn better features.
Okay, thank you. So another question. I've heard that it's common to use neural nets like graph CNNs for drug discovery. My experience with explainability is mostly just with ordinary CNNs, such as with GradCam. Do the explainability methods that you use for graph models naturally extend from such standard CNN explainability approaches, or is interpreting these graph models more nuanced?
Very good question. So you are correct in that most explainability approaches in literature right now has focused on ordinary CNNs, and not only that, just on classification problems, right? So the cool thing that we've been working on was with the quantitative explainability approach that we've created, is that it works for not just ordinary CNNs, but it also works on MLPs, right? So multi-layer perceptron, works on graph neural networks, all sorts of different architectures, as well as also can be applied to traditional machine learning approaches. So I'm happy to share more papers if you contact me, but our approaches allow us to generalize to these different models and different architectures. And it also allows us to go beyond just classification. So we could do things like regression, we could do things like segmentation, we do things like, object detection, and so on and so forth. So again, I'm happy to share more about that work. So the types of explainability that we use, which we've created ourselves, actually allows us to break the boundaries of what existing approaches like GradCam can allow for.
Okay, thank you. The next question is, how quantitative XAI is beneficial when data is multimodal?
Very good question. So again, with traditional explainability approaches, they don't actually work well with, or at all, with multimodal data. So with the type of quantitative explainability that we've created, again, I could share more information about it if you contact me, is that it actually works for multimodal data. And it actually has huge benefits in identifying, because in a lot of cases, you actually get different sources of information. You can't just say, okay, it only leveraged this source of information to make the decision. So for example, in the case I brought up where we have imaging data and we might have clinical data, like is a person smoking, gender, do they have diabetes, so on and so forth. It allows you to actually get the full explanation so that it thinks this person will have, a progression in the disease because of these particular honeycombing patterns in the lungs, and because this person smokes, right? So this allows you to get the nuances and get a full explanation around all of your input data.
Okay, thank you. So I see a question here that looks like a more of a kind of a technical question, maybe to me. So about the opportunities for vendor to beta test and all that. So maybe yeah, please contact me by email and we can see how we can help you on that. Okay, and then I see a question which, well, a comment and a question. Also looks like I can answer this question. Great presentation. That's for Alex. Thanks. Will a recording be made available? So the answer is yes, it will be available on YouTube. And maybe, yeah, maybe that's a good segue. So if you are watching this on YouTube, then please feel free to subscribe. There will be more content that will make available through the channel. And Alex, thank you very much for your presentation. Very nice presentation, and congratulations on all the work that you've done. Thank you everybody for joining and your questions, and we'll see you next month. Thank you.
Thank you. Everyone have a great day.